Welcome back, everyone. In this video, I'll be going over the lecture for the product and quotient rule. Now, just to preview, what are the product and quotient rules? Well, these are pretty much the rules that are going to tell us what to do when we have a multiplication or division of functions and we can't actually simplify it. And after this section, you might just prefer to, anytime you see a multiplication or division, just go ahead and use the product and quotient rule and not necessarily try to simplify first. And that's quite all right. The purpose of last section was really to say, if you are multiplying or dividing things, sometimes you can simplify it. And frequently, when you can simplify it before doing the derivative, it's quicker than using the product or quotient rule. But a lot of times students just see multiplication or division and want to use the product or quotient rule, and there's nothing wrong with that. All right, so let's go ahead and look at the product rule first. So the product rule is going to be the rule that tells us how to multiply functions. When it's multiplied, how do we do the derivative? Well, it says let f and g be differentiable functions, right? All that means is that we can do the derivative of them, and we pretty much only interact with mostly differentiable functions, so we don't really check this in any formal way. We just do the derivative. So every time you see this, just think about, oh, I'm doing the derivative. All right, then the derivative d of dx of f times g, so the multiplying two functions here, f times g, is given by, and we have the formula here, the derivative with respect to x of f of x times g of x equals f prime of x times g of x plus f of x times g prime of x. Now I want to go ahead and improve this, but I think before I prove it, it's probably better just to read in words what this is saying, because the product rule, like many of our other rules and derivatives, pretty much all the derivative rules, it's better to really understand in words what it's saying, because some of them can be quite long like this. So what is this saying? This is saying if you're multiplying two functions and you want to do the derivative, what you do is you do the derivative of the first. That's what the f prime of x means. So we do the derivative of the first part times, and then the g of x, that's just the second part left alone. So just times the second part. Then we add plus, and then you do the opposite thing, meaning we just do the first part, f of x, no derivative on it, and then times g prime of x, which is the second part, the derivative of the second. It's very, very useful to think about the product rule in this way. Now, depending on where you read it, you might actually see this reversed. Because it's a plus, it doesn't matter. So you might see another website, a book, something like that, say, do the derivative of the second times the first plus the first derivative of the first times the second. So basically, this part is in front, this part's in back. But because you're just adding them, the order of addition doesn't matter. I prefer this way because it looks like you do the derivative of the first thing, you leave the second part alone, and then you move on to the second thing and you leave the first part alone. It looks like you're adding up. And that's why I write it that way. All right, now, like with other derivative rules, we can prove them. We're going to prove the product rule just to kind of reinforce two things. One thing is that, once again, this is coming from the limit definition of the derivative. And so it's pretty important to remember that's the background for every derivative rule we get. But another thing is it uses a technique that in math and algebra, you don't really use that often, but it's useful to use sometimes. So what I'm going to do, we're going to have to do the derivative of f of x times g of x. And once again, like with these proofs, you don't have to memorize them. You can just sit back if you want to and watch. But I think it's one of these things that's useful to see every once in a while, especially once you get to calculus. It's good to start seeing proofs. All right, so when we want to do the derivative of something, what that by definition is, we do the limit as h goes to 0 of, and what do we do here? We do f of x plus h, but we're talking about the function here being f of x times g of x, so visually it would be f of x plus h times g of x plus h. We're taking our function, we're replacing x everywhere with x plus h. We subtract off the function itself, which is just f of x times g of x, all over just h. And now here's the thing that I think is really interesting, is that in math, when we try to simplify stuff, we have a lot of ways to simplify it. The oldest way you know is to multiply and divide by the same thing to get a common denominator or something like that. And then you have a couple other ways like factoring and just other ways that you could think of simplifying throughout your mathematical career. But the one I'm about to show you is just as valid as all the rest, and it's just not as used, but it can be useful. So what I'm going to do is take the first part, the f of x plus h, g of x plus h, leave it in the front, and I'm going to write f of x minus f of x g of x in the back here. And what I'm going to do in between is add and subtract the same thing. So if I add and subtract the same thing, it's like adding 0, which doesn't change our fraction, but it's going to help us figure out the derivative formula. So what I'm going to do is I'm going to subtract f of x plus h times g of x. Right? But if I subtract that, because I would be switching the formula if I just subtract it, I'm also going to add it. F of x plus h times g of x. Right, so I'm adding and subtracting the same thing. Now the question can be, why am I doing that? Well, if I can kind of cheat here and look at the formula. F prime of x means I'm going to have a f of x plus h minus f of x over h. So but the g of prime of x also means I'm going to have a g of x plus h minus g of x over h. So I kind of need 4 things. I need f of x plus h minus f of x, and a g x of x plus h minus g of x. Sorry, stumbling a little bit. Right? And so this is going to be the way we do it. Now, what I like to do next here, because this is a fraction, what I'm going to go ahead and do is split it up. Because I know pretty much what I just said, I'm going to have a fraction for the f prime of x part. I'm going to have a fraction for the g prime of x part. And what I'm going to do is I'm just going to split it up by putting the h over the first 2 terms as one fraction. So f of x plus h times g of x plus h minus f of x plus h times g of x over h. So I'm taking the first 2 terms here, writing it over h, and then I'm also going to do plus the limit as h goes to 0, and then I'm going to rewrite the rest over h. So I have f of x plus h, plus h times g of x minus f of x times g of x. And if you want to check that this is valid, imagine if we're trying to go from this way up to here. Remember, when we're adding limits, we can bring the limit on the outside. Or another way to think about it is if you have one limit, you can distribute it to each part. And all we're doing here is splitting up the fraction into 2. So this thing over h is this part right here. The second thing over h is just the second part over h. And think about that as splitting up the fraction like we've done in some previous problems. All right, now why is doing this useful? Well, what we have here, if you look in the first fraction, we have g of x plus h minus the g of x. Pretend the f of x plus h's weren't here, over h. What is that? That's the definition of the derivative when we take the limit as h goes to 0 for g. Now, for the second one, we have a similar thing, but for f, we have f of x plus h minus f of x over h. If we could just ignore the g of x, then that would be exactly the derivative of f of x. Well, luckily for us, the limit rules tell us we can actually basically ignore these. Why? Well, in the first one, I can factor out the f of x plus h. And when I factor it, I'm actually going to write it like this. So I'm going to write it in front, and then I'm going to do a big parentheses for g of x plus h minus g of x over h. So I'm factoring out the f of x plus h in the first one, and what I'm left with is what's underlined. Then I'm going to add, I'm going to do the limit as h goes to 0. And then this one, I'm going to factor out the g of x because that's in common in each term on the top. And I'm going to do it the same way as I did the other one. Write a break parentheses for what's left inside, which is f of x plus h minus f of x over h. Right, and at this point, we can actually do the limit. We don't have actual formulas for f of x, g of x, so we can't conclude anything concrete. But what happens if I plug in h equals 0, or do the limit as h goes to 0? Well, for this part here, the fx plus h, that's just f of x. Now, what happens if I do the limit as h goes to 0 of the thing in the parentheses? Because with limits, I can just do the limit of each part when I multiply. So I can do the limit of this part, which was f of x. What's the limit of this thing as h goes to 0? Well, that's the definition of the derivative of g, so it's g prime of x. Right, that's why the limit is so important. Then we got our plus in between. The next thing we have to do the limit of, we have g of x. Since there's not even an h there, that's just g of x. And then the last part, what happens when we do the limit as h goes to 0 of f of x plus h minus f of x over h? Well, that's the definition of the derivative of f of x. So it's f prime of x. And you'll notice this formula is written in the opposite order like I was describing as before. But because it's addition, you can just rearrange it. So I can put this in front and this in the back. It's just addition. And I can also swap the order of multiplications individually in each one. I can do f prime of x times g of x, which is the same as the second term here, plus the first term, and I can write it in the same order it already is just to match the formula I gave you above. Okay. Right. But the reason I wanted to prove that, once again, it uses a cool technique that you might not use often, but it is something when you're trying to simplify things, especially when you go further in calculus, that you might use in some way. But the other thing is, once again, you really want to know where all these rules are coming from. We didn't talk about the limit definition of the derivative. We didn't talk about all those properties of limits just for fun. It's all working in the background here to make our lives with doing derivatives much easier. All right, but with that said, we mainly want to focus in this course of just practicing doing the derivative, using the rules, and then really building up everything as we go. So at this point, we know how to do the power rule. We know how to do the derivative of e to the x. We know we can split it up over pluses and minuses. And we know the two special derivatives of just x and 1, or just x and a number. Well, now the product rule, we can just add it on top of everything we already know. And now we know how to deal with derivatives if we need to from multiplication. And this first example is pretty much an iconic type of example of the product rule because it is an example that you cannot distribute to get rid of multiplication. What I mean by that is for f of x equals x cubed plus 2 times e to the x, if you distribute it, you still have an e to the x times x cubed, so you're still going to have to use the product rule. There's no way to get around using the product rule for this one. All right, well, what I'd like to do, especially when we're just starting to learn the product rule, is really point out why we're doing the product rule and how to set it up. Okay, so the product rule, like I just described, you can't get rid of it. Can't get rid of the multiplication by distributing, so we are going to have to use the product rule. And the easiest thing to remember is product rule. Product means multiplication, so if you're multiplying functions, you're going to use the product rule. Right, now what I like to do is actually box in, kind of like, or underline, just identify very clearly what am I using as my first and my second part. Well, the first part I should use is the first thing we're multiplying, which is the x cubed plus 2. And the second part is the second part of the multiplication here, which is e to the x. And why I like doing that so much is that when you set up the product rule, if you have this way to read it in your head, derivative of the first times the second plus the first times the derivative of the second, it's a lot easier to just write down and then go through the steps. Now for this one, we want the first and second derivative. And of course, we just focus on the first derivative first. So for the first derivative, because we're going to have to use the product rule, we want to exactly do what I said. Do the derivative of the first. First is x cubed plus 2. And in formula, when we say do the derivative, that means d over dx of x cubed plus 2. Notice I have my parentheses closed here. That means I'm only doing the derivative of this. I multiply the second part, which is e to the x. It's on the outside of the parentheses, so it's just hanging out here. No derivative to do. I add, then I multiply, then I do the first part, which is just x cubed plus 2. Because we're linked by an addition or subtraction here, make sure you write in parentheses. And then I multiply, and I want to do the derivative of the second. And the way we write that, because the second is e to the x, is d over dx of e to the x. Now that you have this set up, what we do is we want to do the derivative of each individual part. We have 2 here. We have to do the derivative of x cubed plus 2 and the derivative of e to the x. Now, once you do these 2 derivatives, once you're like pretty much in the previous section, you know you're done with the derivative when all your derivative indicators are gone. You've done them all. So we have to do the derivative of these 2 things. And how are we going to do that? Well, just now, old rules. The product rule is not adding new rules as far as what we can do the derivative of precisely. It's just telling us how to set it up if we have multiplication. The derivative of x cubed plus 2. We did a lot of practice last section, so hopefully you can kind of just realize the steps we're going to go through here. We do the derivative of each part. The derivative of x cubed is 3x squared. The derivative of 2 is 0, so the derivative here is just 3x squared. We multiply it by e to the x. Then we add. We have x cubed plus 2, which is just by itself. And then we do the derivative of e to the x. And the derivative of e to the x is itself. So it's just e to the x. Right. Now, a big thing when you have the derivative using the product and quotient rules, which we'll see later, is simplifying. And you're almost always going to be able to simplify quite a bit. Not every time, but quite a bit you will be able to simplify. Well, we have e to the x in each part here, so we can factor that out just to simplify. You're not wrong if you stop here, but you should simplify it. Factor out that e to the x that's in common. In the first term, we have 3x squared. In the second term, what are we left with? We're left with x cubed plus 2. I know this is in parentheses, but because it's just got a plus 1 in front of it, if we distributed, we can just get rid of the parentheses and write plus x cubed plus 2. I'm going to get rid of that one just to avoid any confusion. But one thing I want to mention is that this is simplified. Typically, when we deal with derivatives, we like to be factored. Because when it's factored, we could just apply the product rule. When it's not factored, you might still have to use the product rule, but you have to do it more than once. So when it is factored, you only have to do the product rule once. Okay. But another big reason why I would want to simplify this one is we were also asked to do the second derivative. If you do the second derivative and you stop here, it's not that it's going to be more challenging to do than if you do it right here, but it is definitely more work. All right, so let's go ahead and do the second derivative. Now for the second derivative, we want to do the derivative of the first derivative. So visually, we're asking to do the derivative of what's right there. E to the x times 3x squared plus x cubed plus 2. And just like when we did the first derivative, I like to point out what the first and second parts are. The way I have it written, the first part is e to the x. The second part is these 3x squared plus x cubed plus 2. Now, if you wanted to change the order of multiplication because you like having the e to the x second, it is just multiplication, so you could throw it in the back and then do the derivative that way. Right, but what does the product rule say? Because we are multiplying here, we're going to have to use the product rule again. Product rule says do the derivative of the first, but the derivative with respect to x of e to the x times the second, so times parentheses, because I have pluses and minuses, 3x squared plus x cubed plus 2, and then plus, and then the first, which is just e to the x, times the derivative with respect to x of the second, 3x squared plus x cubed plus 2. Right, and now just like last time, once we do the derivative of the two that we've got indicated here, e to the x and 3x squared plus x cubed plus 2, we do those derivatives, and if we can simplify, we will simplify. But after that, we're not asked to do more derivatives, and we're done. All right, the derivative of e to the x is itself. The second part here, we're not doing anything to, so you just write times 3x squared plus x cubed plus 2 plus e to the x, not doing anything to that. And then the derivative of 3x squared plus x cubed plus 2, we do the derivative of each part. The derivative of 3x squared is 6x. We bring the 2 down. 3 times 2 is 6. And subtract 1 from the power. 2 minus 1 would be 1. Hopefully you can see that. Not too bad. And then the derivative of x cubed is 3x squared. And the derivative of 2, just a number, is 0. But once again, we have an e to the x in common. And if you did more and more derivatives with this, because the derivative of e to the x is just itself, you're going to always factor out an e to the x at the end if you kept doing more derivatives of this thing. Right, but when we factor out the e to the x, what are we left with? We have 3x squared plus x cubed plus 2 from the first. And then the second part, we are not, since the e to the x is gone, we don't have any number outside. We can just add it and drop the parentheses. 6x plus 3x squared. And this time we can simplify it a little more here because we have some like terms that we can add together. We have a 3x squared, and 3x squared is 6x squared. Right, that's those two there, and we have no more like terms. It's just plus x cubed plus 2 plus 6x. Now you're more than welcome to leave it like this. I didn't rearrange the first derivative when I got there. A lot of people would prefer to have the powers of x in descending order, which if you want to do is fine. We can just rearrange it. It's all pluses, so it's pretty easy to rearrange. We got x cubed plus 6x squared plus 6x plus 2. All right, so we got the first derivative above. We got the second derivative here from the original function. We used the power rule on both. We got 2 practices in there. And in the next video, we will continue with the section.